As I think the slides are visible to all of you, right? So we'll start with this topic, bargaining. Now, to begin with, it's an integral part of it. It's a regular thing we do in our everyday life, right? And I have given you certain examples, like countries, they bargain over border, China, India, presently. Superpowers, they bargain over nuclear weapons, different corporate houses, particularly during acquisition and merger, they bargain over the actual valuation of particular entity. Political parties go for seat sharing, right? And as you will grow up a little bit more, settle in your life, you'll find that couples, they bargain on it. Okay. The, bar- the bargain is not about maximizing your pay. This is the first thing we should understand about bargain. So far, when we talk about a particular farm maximizes profit, a particular entity, individual maximizes utility, those type of things. At the end of the day, in a game theoretic environment, a particular agent tries to maximize the payoff or the expected payoff if there is certain uncertainty over the results. Bargaining is not about maximizing payoff. It is about devising good strategy. Okay. There are two things which is common across any format of bargaining. First is that suppose you implement successfully a deal through bargaining. What is the counterfactual? That there was no bargaining and it was like a standalone situation. So compared to a standalone non-cooperative outcome, when we talk about bargaining, it is basically we're talking about a such. What do I mean by that? Take, for example, a very non-economic example, absolutely political example. I'm sure that most of you have heard about the Cold War during US and Russia in the 80s. And there was a particular point of time when the entire world stood on the verge of a third world war. Now, why this third world war was most critical, even over and above the first second? Because if you remember the end of the Second World War was Hiroshima and Nagasaki. So when the Third World War starts, it will be purely and nuclear warfare. The entire arc was on the verge of demolition, annihilation. So that you can think of this surreal movies like Mad Max Fury Road, sort of thing. And that point of time I'm talking about is called the Cuban Missile Crisis. US had deployed nuclear capable missiles in its ally Turkey, so that any part of Russia was within the striking range of these missiles. During that time, Russia did not have those intercontinental ballistic missiles which were capable of delivering a nuclear payload in mainland United States. So, under Nikita Khrushchev, USSR struck out a strategy of deploying nuclear capable missiles in Cuba right at the doorstep of mainland US. Now, after successful negotiation, threats, counter threats, all these mechanisms, you just watch, there is a documentary, Discovery documentary on the Cuban Missile Crisis. In YouTube, it's freely available. Have a look. It's a nice watch. It's a pure good thing to enjoy. Now, why I am saying all this? Because had there been a confrontation, which is a non-cooperation approach, or in game theory parlance, a non-cooperative game, I strike, you strike back. What is my best response? I deliver one nuclear head, you deliver two nuclear heads. That will be the Third World War. And who are the players? USSR and USA. Through successful negotiation, what happened? There was no Third World War. There was no nuclear war. In fact, the CTBT, Comprehensive Test Ban Treaty, came after that. And this is the beauty of game theory. You can apply it anywhere and everywhere. If you apply it in a correct format, you'll get amazing results. Now, with that negotiation, there was no devastation. Had there been no cooperation, no negotiation, there would have been a nuclear war. Both the countries would have suffered nuclear stress. So, this no war situation compared to the war situation, there is a sum. And negotiation and bargaining is all about this surplus. Had there been no surplus or excess value, there is no point of any negotiation. This is the first thing. Second thing, it is not a zero sum. I will not say it's always a win-win game, but at max, I can say in a completely generic format, it is not a zero sum. Negotiation is all about dividing the surplus among the two. Now, one might ask, why I should go for negotiation and get a small share rather than as compared to my rival who negotiated and got a larger share. In the Cuban Missile Crisis, USSR got a lower share, USA got a higher share. But why did Russia or USSR accept it? Because what is the other option? What? If I get even a smaller amount of the surplus, that is still a positive gain rather than no surplus at all. Before this entire thing was formalized, people used to call it vaguely the bargaining power of nations or bargaining power of nations. So initially, if we are talking about a time when game theory was not devised or not analyzed formally, people would have said USA had a larger or a more stronger bargaining power. But it's all about a surplus and a division of that surplus. So let me reiterate. Just put it absolutely clear in your mind. One, it is not about maximizing payoff. It is about a surplus and division of that surplus. What is the surplus? Always there is a situation where there will be no cooperation and negotiation, and a situation where there will be a negotiated outcome. So the negotiated outcome is there because there is a surplus over and above the non-negotiated outcome. We negotiate to divide the sum. And hence, it's not a zero-sum game. Both are getting some positive share of the sum. Someone, there is no winners and losers. There are larger winners, there are smaller winners. Now, let's get back to a simple Nash equilibrium concept of this division of something. Just give $1 to two random persons, person A, person B. And the game is very simple. Person A claims a share of that $1, followed by B. Both gets two, both gets their quotations, let me say, or their claims, as long as these two shares add up to anything less than equal to 1. If the sum of their claims exceed $1, both get 0. And this is the simplest form in which you can think of negotiation and buying. So any pair, now we will think of a claim of share X by A and Y by B. As long as X plus Y is less than equal to 1, both gets X and Y, their claims. If X plus Y is greater than 1, both gets 0. So negotiation fails, you get the non-cooperative outcome. Now the question is, why should these two rational agents ask anything about X plus Y which is less than 1? So basically we will concentrate on those options for which the equation X plus Y is equal to 1 is realized. Now, John Nash equilibrium concept will say anything which is X and Y, a pair, adding up to 1, is an equilibrium. So 0.99 plus 0.01 is a Nash equilibrium. Experimental evidence shows. What is the experiment? Say classroom experiment. I just take a pair like Vittal Agarwal and Suryansh Kumar and just ask them, there is 1,000 rupees, divide it among yourself. Most of the time, it's been shown that the area's result is somewhere around 50-50, which is also convergence of expectation. What is convergence of expectation? Suppose A thinks I quote anything more than 50%. Then B can think, okay, why should I get less than 50%? So let's be vindictive, quote something more than 50%. Now, when both of them quote more than 50%, they get 0 at that. Now, both knows that. So even understanding of that will converge the equilibrium to a 50-50 or a 60-40, 55-45. So experimental design shows you that when A claims a share, in general, he does not leave anything less than 25% to B. Now, this is a very vague answer. If I leave it to the Nash equilibrium outcome, this gives basically then we are talking about X and 1 minus X. And X can take any value. I need an outcome. I don't need an array of numbers in front of me. So there are two approaches to solve that. One is the cooperative approach. You sit down together, find and implement a solution jointly. If required, with a neutral third party as an arbitrator. This in general happens when we talk about non-economic issues like the Cuban Missile Crisis. Remember, Cuba, Turkey were also part of that game. Not only that, if you look into that, if you watch the video I'm talking about or the documentary I'm talking about, you will find the Pope. Remember, in in USSR, there's a number, huge, sufficient number of Catholic Christians. Same with USA. So the Pope got involved in entire history that's ever been one part where the Pope sitting on the Vatican City, he appeared and gave public or sent public request to both USA and USSR to stand up. A neutral third party. Other approach is simple and non-cooperative. Now, non-cooperative, as you can see, is easier to implement. Why? I maximize my benefit. That's the definition of non-cooperation. What is cooperation? I maximize the group benefit. It's human nature that individuals tend to maximize their own benefit. Hence, the non-cooperative approach is easier to implement. So even if we look the non-cooperative approach, it is unlike what we have learned previously. It is not about two people or two criminals playing hide and seek with the police in a prisoner dilemma, where they in general take decisions simultaneously. It is about a sequential. I take a step, followed by you, again followed by you. And what are these steps? Offers. I'm talking about a surplus and sharing. So I'm talking about X minus 1 minus X. The moment I declare X, you know what is 1 minus X. Either you can accept that or you can reject. If you reject, then shall I go back to 0 and 0? No, I'll revise X and give you a new X prime so that you know 1 minus X prime. So it's a sequential move which start with offers and counter offers and leads to the equilibrium outcome. So it's not about any X and 1 minus X combination, just like the Nash outcome. No, it's about a declaration. It's every X is a strategy. So X is a strategy of A, Y is a strategy of B. So I say X followed by, you immediately know what is Y, because the moment I declare X, you know Y is equal to 1 minus X. You can accept it or you can give no. I propose Y. The moment you propose Y, I understand what is my pay of 1 minus Y. And this will go on until both comes to an agreement and a particular X and Y becomes the unique equilibrium. So unlike an array of numbers, through sequential bargaining, we approach a definite number. Now, as I said in our lectures, there is no possibility of tutorials, so I bring in a simple example. Let's talk about Andy Grove and Bill Gates. So Andy come up with a microchip worth $900, which he can sell to, say, Intel. And Bill has a $100 worth software package. They meet and they just realize the moment they club this microchip with the software, they can come up with a bundle, combined system of hardware and software, which they can sell at 3,000. So per unit, there is a $2,000 factor. The only thing is how to divide this out. There are different. Let's start in a very non-cooperative fashion. Bill says, look, it is my software which gives worth to this package. Your chip is only metal and sand, whereas silicon. So Andy, you should get $900. I should get 2,001. Now Bill proposes, forget about that. You have devised a software. Fine. It's so simply a set of codes. You get the 100, give me the $2,900. So a third party might say, why are you fighting that? Just split the difference. What is the difference? 2,000 is the surplus. Both take 1,000 each. So one gets 1,100, one gets 19,000. Now, Andy might respond, no, should have equal percentage. Initially, it was 900 and 100. So there is a 9 and 1 ratio of our inputs. So among the 3,000, I should get 2,700 and Bill should get 300. What about an arbitrator? Arbitrator somehow says no. 4-to-1 ratio in favor of N. And you calculate it, you get the profits. So I'm not going through these steps. These are like mere simplest fall of like standard 8 algebra, standard 7 algebra. Okay. It's not about solving. It's all about formulation of the problem. And you can get the exact profit through negotiation. Now, this is a typical example, numeric example. How to generalize? To generalize it, we need to define something called the backstop law or the acronym BATNA. What is BATNA? Best alternative to a negotiated outcome. So in our last example, if the negotiation fails, Andy will sell the microchip for $900, Bill will sell the software for $100. So 900 and 100 are their backstop laws. If the negotiation fails, they do not come with the product of microchip and software together. So they do not get $3,000 per unit, but they get $900 and $100. So now let's redefine what do I mean by that surplus. The surplus is nothing. Take for example, Andy was getting A without negotiation. Suppose $900 I just put A and $100 I put B. So A plus B was their payoff in a non-negotiated situation. In the negotiated situation, the 3,000, let's call that B. The surplus is nothing but B minus A minus. And it is all about this surplus and division, right? Let's get into a very simple mechanic. Everything, the first thing first, the negotiation to hold successfully implemented, both these players has to be given what? Their backstop payoff plus a share of the surplus. Right? So that the share is what? A fraction of the total surplus. But I'm talking about share, the percentage share. So H plus K is equal to 1. Now, what should be the values of X and Y? These are the claims to the surplus. So X should be A A was Andy's backstop, that $900, plus H fraction of the surplus B minus A minus B. Similarly, Y will be B plus a K fraction of the surplus. Now, what do I know? H plus K is equal to 1. And the surplus amount is the common V minus A minus B. So you get the ratio X minus A divided by Y minus B is equal to H by K. Or you rewrite that as Y is equal to a function of X. So for any particular surplus value V, the share claims H and K should be such that this equation Y is equal to, look at the right hand most part of the equation. It's nothing but rearrangement of these equations. So first, you get an equation Y as a function of X. You can think it in terms Y as the best response to any particular X that you quote given H and K values. H and K are parametric values. One more, X plus Y should be equal to V. So I have two unknowns, X and Y. You have two equations, 1 and 2. Solve it. How do they look? They look like this. Look, I started with their backstop uh, payoffs B and A. So point P, the coordinate P, indicates the backstop in payoffs in the payoff space Y and X, right? H and K determines what? The slope. What is the maximum that both can get? V, the total surplus. And that is why you have a 45-degree line, VV. And then these two equations will intersect, and graphically you can say Q will be the equilibrium. Right? Now, it seems so easy, right? So let me skip a little bit part of it. Just let's think about a different scenario. Is it possible to jointly maximize? So far, what we have done, it's a non-cooperative outcome. Look at the second equation, Y as a function of X. It looks exactly like a response function or a reaction function. Whatever X you choose, I have a Y to maximize my payoff, right? And I have a constraint. So it's basically a constraint optimization problem. The question is, so far, this is a non-cooperative approach. So the question that is required to be answered is, what if giant action was? And not I choose a Y contingent upon your X, but we sit together and we somehow jointly come up with the outcome. So I will just skip certain portions here. These are like theoretical understanding or philosophical understanding of how non-cooperative thing is being modeled and what is the efficient part of it. I'm just skipping it for the time. Now, if you look into the optimization problem, when I said it's basically a constraint optimization problem, basically you have a format in this. So you have a joint maximization. X minus A is X was my share, minus A was the backstop. H is the fraction I quote. x minus a to the power h into y minus b to the power k, subject to y is a function of x, right? And from the first order condition, what do you get? It get exactly the same equation. That, what is this equation? X by y is equal to h by k. Look, same equation. So whether you model it in a non-cooperative fashion or you go for a joint maximization, the moment you have a non-cooperative approach, the Nash equilibrium will be the same formula, right? We have taken a non-linear format. So now you have utility frontiers and you have a non-linear constraint function. That's it. That's the only difference. Now, more important thing is that under this backstop payoff and negotiation, non-cooperative negotiation, or the Nash outcome of this bargaining thing, can I use my payoff by changing my backstop payoff? This is exactly what we call the variable threat bargain. Why variable threat? I vary my non-negotiated outcome in the bargaining process with a threat that the bargaining or the negotiation process will collapse. How? It's very simple. So let's start with the initial backstop payoff A and B, the coordinate being showed by the point P. Q was the equilibrium. Look at all the points P1, P2, P3. In all the cases, A, individual A, whose share is X, is better. How? There are three ways. So starting from, look, we have not changed K and H. K and H were the shares we claim. Without changing the claims or the shares, just rearranging our backstop payout, we can be better. How? Player A can choose a point P1. What is P1? He can say, look, you think A is my payoff? No. I have a payoff A prime, which is much better more than A. It's not $100 I will get. I will get at least $300 to $400 for my software. So you increase your payoff, P1. Then you go to Q prime. Other way, you decrease your rival's backstop. So A says, look, you are claiming that B is your backstop. No, it's much lower. So the basically we should concentrate on the point P2 and hence Q prime. More interesting, I can reduce both our payoffs. So I'm not increasing my payoff or decreasing your payoff, but I am decreasing both our payoffs, but trying to locate the point at P3. Even they'll get in P3. What are the practical applications? Take for example, when he said, let's move to P1. You will always be able to negotiate a better job offer if you have one good offer in your basket. Or you can say the point P2. Take for example, you make yourself so valuable to the company with your employer. You can say the moment I leave, you lose a lot. So look, the threat is there. It's all about devising this threat mechanism. Now, so there can be other ways of modeling negotiation. We said no, it's all about offers and counter offers. So let's get back to that. So we start with a very simple situation of alternating offers. So we start with A giving an offer, B accepting or rejecting or giving a counter offer, and move on until and unless we reach an equilibrium. And the enter is a backward induction solution. We get to the subgame of equilibrium. Okay. Now there are questions which we need to answer before we start this model. The first is, okay, we're talking about offer, counter offer, and it goes on indefinitely. We start at the end point, solve the stage, one stage back, then again one stage back. So we go on a backward induction, and then finally we solve come at the equilibrium. So we must start at the end. The question is, where is the end point? Even more important, why should to have an endpoint? That means this negotiation or bargaining, this process is terminated. So why should this process terminate at all? What even? Why should it even start at all? What if they stick to their original positions? I give X, you give Y, X plus Y is more than surplus. Negotiation outcome, not none of the equilibrium. And I refuse to budge. You also refuse to budge. Then what? Understand that we must bring in a concept that if it fails, so first we answer that why should it start? It start because we need to negotiate. Why negotiate? If we do not negotiate, the entire surplus is lost. Fine. Second, why should it terminate? If it does not terminate, again the surplus will be lost. Next, why should we budge? Or the process of offer and counter offer occurs in the first place. To bring that, we should understand that the more time we take to negotiate, the surplus value shrinks. And this is basically what we call the decay. The more we wait, the more we negotiate, the surplus shrinks. And time has value. And in this case, patience or impatience, both are very important. And if you delay the agreement, both will get lower shares. Okay. Now, to give that again an example, take for example, American football, 4 quarters. I'm a fan of one of the teams. I want to watch live on the stadium. I reach there, ticket is sold out. I find one blacker who has one ticket. He is willing to sell it to me at a price, and I must purchase that, giving him some dollars. What is my backstop? Just opposite the stadium, there is a pub where I can have a beer and watch the game live on a giant screen. The problem is, I would prefer to be in the stadium because I'm a hardcore fan of, say, the Rangers working. The maximum which I can pay is $25 a quarter per quarter. This is the 4 quarters, 15 minutes each. Okay, so that's the story. Just remember, I go before the game starts. What is the value of the ticket? The maximum. Suppose I give an offer. Okay, this the particular blacker tells me, okay, this much you should pay. I can accept, or I can go back to the pub, watch it there. Again, just before the second half or the second quarter, I come back and renegotiate. As the game approaches the end, the value of the ticket falls. So from here, can anyone tell me what would be, with the information on the screen right now, can anyone tell me what would be the equilibrium price of the ticket so that the blacker will sell and I will buy and watch it live on stadium, the entire game? I will just take 1 minute, or rather, I'll give you 1 minute to answer, to try. The first hint is, what will be the value of the ticket at the beginning of the fourth quarter? Zero. If the negotiation fails, I go back to the pub, the blacker gets zero because there will be no value of the ticket after the fourth quarter starts. Revise back. So the blacker knows that if I come at the beginning of the fourth quarter, he has to give it to me free. There is no reason for him to hold the ticket. Revise that information at the beginning of the third quarter. So jointly, for the third and fourth quarter together, he can charge me $25 because he has to give the fourth quarter to me for free, right? Go back one period, please. If at the beginning of the second quarter I leave, that means I do not accept the offer made by the blacker. Then at the third quarter, you have to be you have to give it the ticket to me for $25. So you will give me the ticket at $25 even at the beginning of the second quarter. First quarter, another $25. $50, it will be done. What is the surplus? I was willing to give. So what is the value of the ticket to me? 4 quarters, $25 per quarter, $100. So that's the surplus. How it is being shared? I give $50 and I watch the game for the entire game. So basically, $50 to me, $50 to me. So even before the match starts, both these players can foresee the entire future, roll it back before the game starts. The ticket will be sold at $50. Without doing a single match, we can solve it just through simple logical deduction. Now, You generalize that theoretically. I make an offer. So the source total surplus, I make an offer X1. If you accept, done. If you do not accept, then the value of the surplus comes down to V minus X1. Such that, let's assume, make it finite. You can make it infinite also. So there will be del 1 minus del square. So basically it's 1 minus 1 minus del. So you can do that infinite discount also. But let's make it simple. Suppose for 10 rounds, this offer can hold such that X1 is by me, X2 by you, X3 by me, X4 by you. So if all these offers and re-offers, counter offers keeps on going, 1, 2, 3 is time period. The first period offer, second period offer, third period offer, 10th period, there is no surplus there. And if I give this problem to you, what will be the equilibrium where there will be no decay? The entire surplus can be split. Look, if the gain reaches the final period, what is the value of the surplus? X10, because that's the only thing left. Who is making the offer? B is making the offer because it's the even, odd. So first by A, second by B, third by A, fourth by B. Offer, counter offer. So it's the even, 10. So B makes a final offer and can take the entire surplus. Roll back one period. It is X9 plus X10. Now, A knows if he does not offer at least X10 to B, B will not accept because he will get X10 in the next period. So I keep X9, give X10 to B. Roll back one period, and this is exactly how it will look. So in the very first period, A makes an offer where he keeps and he gives, and B will offer, accept this offer. Now, here we have not used any backstop here. If you just bring in backstop, nothing. Suppose small a is the backstop for B. So X10 minus A instead of X10. That's the only difference. Now, there can be two types of decay. The thing that we talked about is a gradual decay. There can be a sudden decay. And this is what we call an ultimatum. Okay. Now, there is a proposer and there is a chooser. Let's come back to that $1. Most, even in that ultimatum, what will be the case? What is ultimatum? I make an offer, you accept it, or both of us gets nothing. That's the sudden decay. So there is only one offer to be made, which is to be accepted or rejected. The moment you reject it, everything is lost. So there is a proposer and the other one is a chooser. Now in this case, basically what happens, the proposer is more like a dictator. Either take it or leave it. But even then, the experiment, particularly classroom experiments, the most common offer was a 50-50 split. Now, interpretation of this, you could have just take 99% and leave 1%. Take it to leave it. It's a dictator format. Then if this is the theory and these are the evidence, how do we correlate? The college students cannot calculate. No, they can calculate much more complex things than this. Basically, in this type of environment, look, environment is very important. We are talking about college students and we're talking about a dollar. And both of them know it's a part of an experiment. So the sense of fairness is very, very important to students. Anyway, so let's come back to the impatience and the last version of this alternative offer model. And we call it an impatient. And we bring in a what we call a deflator or what we call a discount factor. So a dollar today is better than a dollar tomorrow. That's the concept. Because there is a time value of money. I prefer a dollar today rather than getting the same dollar tomorrow. And it is true for everyone. Let's assume both of the players prefer 95 cents today rather than a dollar tomorrow. Not only that, a dollar today is better than a dollar tomorrow. I am willing to take 95 cents today rather than waiting for tomorrow and get a dollar. Basically, we're trying to quantify the degree of impatience. There are two reasons for this impatience. One, there is obviously a rate of return. If I have a sum of money today, I can invest and get a return out of it rather than waiting for a time period to be over and getting the same money. Because a dollar today can fetch me something positive, however small, than over and above a dollar tomorrow. So that's the rate of return. Second, there's a risk that the game might not continue tomorrow. It might not continue. The game might not exist tomorrow. So it's better to get. So how much am I willing to sacrifice so that I get the share today itself? So while we are trying to quantify, it's very simple. That 95 cents is better than a dollar. I prefer 95 cents today rather than a dollar tomorrow. And we start with a very simple, no backstop, zero backstop. And we come back to the $1 divided. A starts the process. A offers X, right? And in the next period, B will accept or give a counter offer. Now, this proposer must give, or the initiator must give the opponent or the rival or the other player at least an amount which is equivalent in his eye. So if I want to give him X tomorrow, I must give him at least 0.95X today. So if I offer 0.95X to B, I am left with 1.095X. But who makes the offer? A. What was A's offer? X. So we equate. So X is is equal to 1 minus 0.95X. Or X is equal to 0.51. First thing, that this will be accepted because B is willing to get 95 cents today rather than $1 tomorrow. He's impatient. And we don't have to go through this. Remember the questions, how long it will go on? Where is the end? How long the process will continue? The process will not continue. The process will start and end there because everyone can foresee the future. And everyone is worried about the cost of delivery. So it's better to give an offer which B will not reject. And hence, the maximum value V, the surplus, is being distributed rather than a decayed value of V in later period. Second thing is the person who makes the first offer gets marginally more. So in a dollar division, A gets 512, B gets 480. Now, what if these two players are not equally impatient? One is more impatient than the other. So we still continue that B regards 95 cents today is equal to $1 tomorrow. But A himself is more impatient and thinks 90 cents today is equivalent to $1 tomorrow. So A starts with an offer X. And if B starts the offer, he will start with an offer Y. Now, what does A know? That if B starts the process, he will give Y, he will get Y in the next period. Suppose I start with X today. B rejects, B will give an offer Y tomorrow. But if I can give Y 95% of Y today, he will accept. So X is equal to 1 minus 0.95Y because I'm giving him right now 0.95Y out of $1. So I'm left with 1 and that was my offer. My offer is X, which is this. So I get the first equation. Similarly, just think in terms of B. He starts with Y. He knows if A does not accept it, he will give X in the next offer X. His offer will be X in the next period. So if I can give him 0.9 of X today, he will accept it. So you have two unknowns, X and Y, two equations. Solve, get the values X and Y. So if A starts the process, A will give X and 1 minus X. If B starts the process, B will get 0.69 and 0.3. Now look, in both the cases, A gets half almost that of B. Why? Because A is more impatient. So that's the price of patience. Okay. Now, if we generalize this model, instead of 95%, 90%, let's make it some generic 1 by 1 plus R. And for B, 1 by 1 plus S, R not equal to S, assume R greater than S. Solve for it, you get these two equations. Now you can ignore the multiplicative term R into S. Because what is R? If I assume 90 cents today is equivalent to $1 tomorrow, then basically I'm talking about an R which is 0.0 or 0.1, sorry, and 95% 0.05. So 0.1 into 0.05, it's a very small amount. You can ignore that R is coming. Okay. So observation, x plus y greater than 1. Why? If you just look at this, the problem is, do not misinterpret. When I'm talking about X and Y, basically these are the two beginning offers by the two different individuals, A and B. If A starts, then the share will be X and 1 minus X. If B starts, then it's Y and 1 minus 1. So do not assume that X and Y are the two offers coming together. It's either X and 1 minus X or Y and 1 minus Y, not X and Y. Second, as I told, you can ignore that RS. Third, the moment you come to the approximate solution, removing the multiplicative term RS, what you see? X by Y or Y by X. What are these? These are the initial offers if either A or B starts the negotiation process. That is nothing but a ratio of their degree of patience, R1. So the share that I get is inversely proportional to the rates of my negotiation. So the more patient I am, more share I will get. Okay, so that's all. And this is the reference. So let me stop sharing the slide. Open to questions. Okay, if there are no questions, then Shayantan, I will request you to stop recording.
Yes, sir.
Then